Good afternoon. So today we will obtain the general solution of the wave equation using classical functions. This is actually a rare treat, as you will see later on, because normally we can't find solutions of partial differential equations in terms of classical functions, or in general it's not an easy feature. Series representations come to a rescue to solve not only the PDE itself, but the boundary value problems. Because you will see with the example of the wave equation, the pesky boundary conditions are what make the problem even more complicated. So as it turns out, the wave equation and also a slightly larger class of linear equations, if we just want to solve the equation itself and we don't worry too much about initial conditions, the general solution, it's not that difficult to find. So in fact, there is a recipe of finding these solutions, like I said, for a larger class of linear equations. The problem is those general solutions are pretty much useless if they don't fit some sort of initial or boundary conditions. The more restrictions you have with those conditions, the more difficult or impossible it is then to actually come up with a useful solution. And you will see immediately what we mean as we move along with actually finding the general solution of the wave equation. So the objective, just to summarize, will be to actually solve the PDE itself. So we're not going to worry about initial conditions or boundary conditions. Then we're going to impose some conditions, but not too many of them. So we will still basically move on to a easier problem, just with some conditions attached to the PDE itself. And then maybe on the next lecture, we will see how we can use these general solution to find solutions of boundary value problems. Again, under some limited situations, because in general it doesn't work for all possible boundary conditions that you can come up with. For this lesson, we just have to basically remember some notions from calculus 3, namely the chain rule for the functions of several variables. And what we're going to do, basically, we're going to make a change of variables, essentially. And by that change of variable, the equation itself becomes a straightforward equation to solve, as you will see. So we're going to make the following change of variable. And remember, here y denotes a function of little x and t, right? The displacement at location x and time t for our vibrating string. And the change of variable is that u will be x plus at. A is related to this coefficient here in front of the Laplacian, and then y equals, v, the other variable v equals y, x minus at. And you should see basically already why we prefer to denote this constant in front of the Laplacian by a squared, because this change of variable is much more straightforward. Otherwise, if I use a different letter than a squared, this transformation would involve a square root of a constant, and it looks a little bit tedious if we do that. So that's why it's customary to denote this constant by a squared. Okay, so we're going to change essentially, the goal is to change these partial derivatives with respect to t and x in terms of partial derivative with respect to u and v. So that's what we want to get. And from calculus 3, remember, if you have a function of two variables, which in turn each of them is a function of other two variables, you have what we called in calculus 3 like a tree of dependence of these variables. So view first y as a function of u and v, which in turn is a function of x and t, because u is x plus at, v is x minus at. And remember, from the chain rule, y partial t is going to be y partial u times u partial t plus y partial v, and then y v partial t. So basically you go with partial t via partial u and v first. Right, so that's the chain rule for a function of two variables, basically. Okay, now u partial t, just take a look at these transformations. U partial t is a, so this is going to be a times yu, and then v partial t is minus a, so that's going to be minus a y partial v. So if I factor out a, this is y partial u minus yv. Eventually we have to replace, remember, the second order derivative with respect to t in the wave equation. So we have to do partial t one more time. And now each of these two functions, partial u and partial v, splits again into a sum via the chain rule. So look carefully here, a is a constant, that comes out. And then now we do partial u again, so that's going to be partial u twice, and then via the chain rule, multiply again by u partial t plus y uv, and then vt, and then same thing for y partial v with respect to u first, then partial t, there's a minus in front of it, plus y v twice, and then v partial t. All right, so let's replace again the u partial t and v partial t's by a and minus a. So this is going to be a y u twice minus a y u v. Then we're going to have minus a y v u minus is going to be minus a, because vt is minus a y v twice. Okay, let's see, we can simplify this a little bit. We can pull out a, so we're going to have a squared y u twice minus y u v minus y v u plus y v twice. Now another thing from calculus 3, remember, if the function is differentiable with continuous derivatives, which we will assume here basically, the mixed derivatives are equal. So we can assume that uv, partial uv is partial vu. So these two are equal. So we can combine these two into minus 2y partial uv. All right, so then let's write it down from the beginning. Y partial t twice, this is a squared, y partial u twice minus 2 y u v plus y v twice. All right, so let's keep this in mind. And now let's do the same thing for the right hand side of the PDE, yxx. So starting with yx, make sure you do this computation on your own and check with me, because you're going to have a homework problem where you have to do the same type of chain rules. Always go slower, remember. So partial x again is going to be y u, but then times u partial x plus y v partial x. Things are a bit easier here because u partial x is 1, v partial x is 1. Just go back here on the top and look at the transformations. Partial x1, partial x1, v ux and vx. So this is just yu plus yv. One more time with respect to x, this is going to be yu ux, yu, right, times u partial x plus yu v vx, y vu ux, and then y v vx. Again, these are equal to 1, and these are equal as well, uv and vu. So therefore y x partial x twice becomes y u plus 2 y u v. It's very awkward to read this stuff. I'm trying to use shortcuts so that it doesn't sound like mumbling. Sounds like you sound like a crazy scientist. U v v and so on. Anyway, so this is y partial x twice. Okay, so then what does the PDE become if we replace ytt, yxx with this equivalent expression in terms of u and v? Well, we're going to have some nice cancellations, as you'll see immediately. So on the left side of the equation, so now let's plug into the wave equation. So on the left side, we have a squared and that big parenthesis. On the right hand side, we had already a squared in the equation times yxx, which is replaced by its equivalent form in terms of u and v. Okay, so a squared cancels. We can divide both sides by a squared. Yu twice cancels out. Yv twice cancels out. And then we can move these two to the right hand side. And so the whole equation becomes 4 yu partial y partial uv equals 0. So of course we can divide by 4 and the whole PDE boils down to partial uv equals 0. That is really neat. And as I said before, you will have to go slow with a homework problem which essentially shows that a large class of problems, we're going to have a classification of these problems later on, are amenable to this type of work, in the sense that under suitable substitutions, and the good news is that you will have a recipe for those substitutions, which is neat. So under some substitutions, one can reduce the equation to a simpler form that can be integrated. That's the key thing. So now I view the dependent variable y as a function of u and v. So if the partial uv equals 0, then I can just solve for y. But look carefully how I do this, because remember, this is basically integration with respect to two variables, or to one variable at a time. The external, the outermost derivative is with respect to v. So if I integrate both sides with respect, both sides with respect to v, this is just calculus 1 integration. I eliminate the partial v on the left side. Now the integral of 0 with respect to v, that's just going to be a constant, except that notice that constant may still depend on u. So it can be just a function of u. On the left side, you're left with y partial u. Again, if it's not clear, you could do this mentally. It's not a big deal. This is just a very quick calculus 1 checkup. So if I do partial v on the left side, that's going to be y uv. Partial v on the right hand side is just 0, because the right hand side depends on u. So you can just assume it's just a constant, like a real number. It can be a function of u. So constant with respect to v. Don't forget that we have two variables. So this is like partial integration if you want. Moving on, to get finally to y, I need to integrate both sides now with respect to u. This is u here. So finally on the left side, then I get y of uv. On the right hand side, we have this antiderivative plus a constant of integration, but that constant can depend on the other variable. I can't assume it's just a real number, so it can be a function of v. Let's just call it g of v. Just to make things easier, we're gonna make a renotation for these functions because I don't want, we don't want to keep the first piece in terms of an antiderivative. So that's just gonna be basically an antiderivative with respect to u. That's just another function of u. So we can rename this and to use the notation in the book, a function called phi, big phi of u. And just to have some consistency with the Greek letters, we're going to denote this by psi of v. So this is kind of anticlimactic probably, but the idea is that really the solution of the wave equation in terms of u and v is just some function of u plus some function of v, under appropriate assumptions like differentiability and all those good things. Now on the second page, I'm going to rewrite this in terms of our original variables, because our problem is in terms of x and t, and then we're going to make some comments about the meaning of these, and we will have probably a presentation with Maple just to illustrate the meaning of this solution. But stay tuned for the second page. All right, so to review from the previous page, we just concluded that in terms of u and v, those new variables, which remember came from this change of variable, x plus at for u and x minus at for v. So we concluded that the solution of the wave equation, the general solution, is just the sum of two arbitrary functions of a single variable, one in terms of u, the other one in terms of v. Again, if you don't believe it, remember it was came from u yu partial v equals 0, and it shouldn't be hard to realize that if I do this partial v first, that's gonna essentially kill the first function. Phi of u disappears and you're left with this. And if the answer, you do it again with respect to u, so partial u, this is going to be 0. This will be a function of v with partial the other variable, that's going to be 0. Now, of course, in terms of your original variables, so to go back to your original equation, so if your equation is stated as originally written in terms of x and t, then your solution as a function of x and t is some function phi of u, which is x plus at, plus some other function psi x minus at. There is a neat interpretation of this solution if you were to sketch it and let t go to infinity. Because of this argument, x plus at, x minus at, and also remember that when you have a shift like this, for example, if you were to sketch phi of x minus at, so what I want to say is that these two functions are called traveling waves with speed a, right, a times t, that denotes the speed at which they travel to the right or to the left. The idea is like this: if you were to sketch phi of x, let's say phi of x is like that, psi of x, I'm sorry. X minus at means a shift to the right hand side. So basically this is like a wave that travels to the right, and this one travels to the left. So you can interpret the solution as being a summation of two waves that travel in the opposite directions. We'll look at some intuitive examples with Maple later on, but this is basically the connection with the, that's why you can make this analogy, because of this argument, x plus at, x minus at. So x minus at implies a shift to the right, so as time goes on, that shift continues to move to the right hand side. That psi of x keeps on moving to the right hand side. And at the same time, phi of x plus at keeps on moving to the left side. This is just really boiling down to how we obtain the graph of a function from another function by shifting the argument. You know, people do not remember in pre-calculus those typical problems when you are given the graph of a function and you need to sketch the graph of the shift of that function to the right or to the left. These two functions are called traveling waves. Now notice again, let me write it again here, this general solution is pretty useless unless we find actually what these functions are from initial conditions and or boundary conditions. So this is true, remember, for pretty much all PDEs, right? I mean, the general solution typically depends on an arbitrary function. So that's not really useful if you want to do something in real life with this PDE. And in real life, you don't have just the PDE. You also have some initial conditions, some initial state of the experiment, which if they are all established, they should give you a mean to actually find what these functions are, these phi and psi. So fortunately, and we're going to do this also in this lecture, in some ideal conditions, we can actually solve for phi and psi. And here are what the ideal conditions, which are essentially the easiest ones in the wave equation that allows you to quickly find phi and psi. So suppose you have an infinite wire, or an infinite, like we call it, an infinite vibrating string. Meaning that it's so long that it doesn't really matter what happens at the endpoints, and you're looking at just what happens at a small portion of the string. But it's so long that there's no restriction at the endpoints. This is essentially, of course, an approximation of reality. There's no such thing as an infinite wire. But for practical purposes, let's say that that's the case. So essentially, we have no boundary conditions. There's no limit for x. X is between minus infinity and infinity. And the only thing we have some initial displacement and initial velocity. Right, so this string is deformed, but again, it has infinite length. And this deformation, this initial displacement, is given by a function. So let's say y of x0. So at time 0, the displacement is given by some function. So this f of x is known or given. And again, to make things easier, let's say the initial velocity, which remember is given by the derivative with respect to t at time 0 of x, so y partial t at x0. Let's say the initial displacement velocity is 0. So on the second page, because I don't want to squeeze it here, we're going to find out actually what phi and psi are. So let's stay tuned for the next page. Okay, so let's impose these initial conditions and see if we can find a phi and psi. So we're going to go slow, and we're going to have a homework question similar to this. So pay attention how we get to find this phi and psi. Now remember, we find unknown functions here. So the goal is to basically find what phi of the argument is. Then later on, you're going to plug in x plus at in the solution. So the key thing is that if I find a formula for f of y, or f of x, whatever, then you can replace later x with x plus at in the solution, right? If when the time comes. The goal is to have a formula for the function phi and psi. So, and remember the little f of x, this is given, this is the initial displacement. So let's plug in t equals 0. So we're going to impose the first condition. So y of x 0 equals f of x. Well, y of x 0, if I replace t with 0, that means phi of x plus a times 0 plus psi of x minus a times 0 This is the given function f of x. So the first initial condition gave me the sum of the two functions, phi of x and psi of x. So we're going to keep this in mind, because if I'm lucky to find another relationship between phi and psi, then I can find the two functions. Okay, how do I impose the second boundary initial condition? Well, I need to take partial t first, so look carefully here. We do partial t in the solution, and then we plug in t equals 0. So partial t of xt. Now we use the chain rule. Remember, phi and psi are functions of a single variable, so it makes sense to use the prime notation. So phi prime of whatever is inside times the derivative of the inside with respect to t, which is a, plus psi prime of x minus at, follow up with the chain rule, the derivative with respect to t of the inside, which is minus a. Now, finally, we plug in t equals 0. So y partial t of x0 is going to be phi prime of x plus a times 0 times a on the outside, minus, we can take the minus out, phi prime x minus a times 0 times a. So if we simplify, this is a quantity phi prime of x minus psi prime of x. And remember, this is equal to 0 because I made it so, right? I said the initial velocity is equal to 0. Okay, so we can divide by a. There's 0 on the right hand side. So if I divide by a, then the second condition boils down to phi prime of x minus psi prime of x equals 0. Which, if we put it in the single derivative, we concluded that the derivative of the difference between phi and psi is 0. And we know from calculus 1 that that means the function itself, the difference between phi and psi, must be a constant if its derivative is 0. All right, so I hope you go slow, pause as often as necessary. It's not that difficult, but there are lots of different steps to take care of as we move along. So together we have two conditions, right? So from the first condition gave us the sum equal to f of x. The second condition gave us the difference between phi and psi, which ended up being a constant. So we can solve now for phi and psi, just like we solve a 2 by 2 system. If we add the two, that will eliminate psi. So we have 2 phi of x equals f of x plus c. Divide both sides by 2. That gives me phi of x 1/2 f of x plus c over 2. Now we can go back to one of these equations and find psi. So we can go back to the first, plug in 1/2 f of x plus c over 2 for phi, and then get psi by itself. So psi of x is going to be f of x minus, move this to the right hand side, minus 1/2 f of x minus c over 2. And together f minus 1 over 2f, that is another 1/2 f of x minus c over 2. C is still not determined for now, but you'll see it's not going to matter in the end. Okay, so we just found the two arbitrary functions, which are no longer arbitrary. So from those conditions, from this initial condition, from initial displacement and 0 initial velocity, we concluded that phi is 1/2 f plus c over 2, psi 1/2 f minus c over 2. What is the actual solution of the wave equation? So let's not lose sight of this corner on the left side here. where I point the arrow here, right? Because the solution is phi not at x, but at x plus 80, and psi not at x, but at x minus 80, and add it together. So we need to plug in, and let's write down now the solution. So we need to plug in x plus 80 into phi. So that's going to be 1/2 f of x plus 80 plus c over 2, to which we add psi at x minus 80. So we plug in x minus 80 here into psi of x, and then minus c over 2. So again, this is phi of x plus 80, and this is psi of x minus 80. Is the other traveling wave. Now c over 2 happens to cancel, and therefore we concluded finally that the solution of the wave equation is 1/2 f of x plus 80 plus 1/2 f of x minus 80. So if you have an infinite wire with f of x being the initial displacement, and 0 initial velocity, then the solution is given by these two traveling waves given by that initial displacement. Half of it moving to the right, half of it moving to the left. And it's a great thing basically what we achieved right now. Essentially, if you have that infinite wire, okay, let's end up with a quick example. If someone says, okay, you have an infinite wire, endpoints don't matter, no restriction on the length. And then let's say the initial velocity is equal to, the initial displacement is given by, let's say, x squared. Really kind of unrealistic, because if you think how this looks like, it's like an infinite parabola, right? So it's just, a wire that descends from infinity for the endpoints, essentially. And then initial velocity equal to 0. I'm going to show you basically with the demonstration in Maple a slightly more realistic displacement. But like I said, you are given a displacement, which is a function of x. You are given the velocity, which is equal to 0. If that's the case, then you can just go right away and say the solution of the wave equation. And by the way, let's say, just to make it nice, let's say a equals 1. So let's say the wave equation is ytt equals yxx, right? So that coefficient a is equal to 1. So then you can write the solution to be 1/2 x plus t squared plus 1/2 x minus t squared. You can simplify that later, or you can leave it like that. So in other words, you can just plug in x plus 80, x minus 80 into the function that gives you the initial displacement. So I think that's it for today. The next lecture should be, not lecture, but the next portion should be a demonstration. I mean, not demonstration so much, but examples done with Maple, so we could see some graphs and understand this analogy with the traveling waves. So that's it for today.